we're looking at triangles. So we can identify triangles by their sides and by their angles. So in a triangle, we have these things called vertices. A, B, and C are all vertices. And those vertices, they're angles, or they create angles, and then they're associated, and I should have done these in different colors, with the sides across from them. So here I'll do A in red. And that's why the side across from that angle is little a. B, the side across from it, that's why it's labeled little b. Then same for C. Across from it is little c. So if A was the largest angle in the triangle, then side A is going to be the longest side. Right? So there's three kinds of angles within a triangle. All the angles could be acute, so under 90 degrees, and then we will call that an acute triangle. Or there could be one right angle in the triangle, and we'd call that a right triangle. Or we have an obtuse triangle. So if we have one angle that is obtuse, we'd call it an obtuse triangle. All right, we can do it by side lengths as well. So I think one that you're probably used to seeing is an equilateral triangle. It means that all the sides are congruent. And if all the sides are congruent, then so are all the angles. So equilateral. If two of the sides were the same, so these little tick marks mean that they're the same length, the sides match up with the opposite angle. So if the sides are the same, these angles are the same as well. And having two of them would make this an isosceles triangle. And the only other option is that all three sides would be different, which means all three angles would also be different. And that's called a scalene triangle. Right? Sorry, my tablet just fell. All right, let's see. We can find the measures of angles within a triangle because all angles in a triangle are supplementary, meaning they add to 180 degrees. So in this triangle, I can find the measure of all of those angles because I know that all of them added together, so x plus 17 plus 3x minus 62, all of those equal 180 degrees. So I can add my like terms, so x plus 3x to give 5x. And I can do my other like terms, my 17 and my minus 62. It's negative 45. Those equal 180. And then I'll solve for x. So I'll add 45 to both sides. And then I'll divide both sides by 5. Let's see, 225 divided by 5 is 45. And now I can find all the angle measures. So this one's the easiest. It's just what x is, which is 45. This one is 45 plus 17, which is 62. And then this one I have to do 3 times 45 first. So 3 times 45. And then I'll subtract 62. So I get 73. Then we can double check that 45 plus 62 plus 73 equals 180. And it does. So then we're done. All right, so let's see if we can solve this one. We got a bunch of triangles here. And we can use our angle relationships to help us out as well. So, this is what I'll do. So I don't think your textbook talks about this theorem, but I'll tell you what the theorem is anyway. So in a triangle, and I'm going to do this off to the side, we have a triangle. If I extend one of the sides, this is called an exterior angle. And there's a theorem that says, that let's say this is angle 1 and this is angle 2, and we'll say that's angle 3. There's a theorem that says that the measure of angle 1 plus the measure of angle 2 is going to equal the measure of angle 3. So I can add these two together, and I get this third one. If you don't remember that, we can work a little backwards, because like the measure of angle 1 is going to be 30 plus 89. So that's going to be 119. And if you don't remember this theorem, it's okay, because here's what I can do. I can have a totally other relationship. So this is a triangle here. So all three of these angles add up to be 180. So 30 plus 89 plus that question mark equals 180. So 30 plus 89 is 119 plus something gives me 180. So then 180 minus 119 is 61. So this question mark angle here would be 61. And then the relationship between these two angles here, 61 and angle 1, they make a straight line. So I would subtract 61 from 180. Well, if I do 180 minus 61, I get the same thing of 119. So it takes a couple extra steps to have gotten that 119 without that theorem. And that's okay, because we needed to get this mystery angle anyway, because it's a vertical angle to angle 2. So angle 2 is also 61 degrees. All right? So I can use either the theorem that angle 5 plus 75 is going to equal 134, or I can say, hey, these two angles make 180. So this can be 2 question marks. So 2 question marks plus 134 is 180. So subtract 134 from both sides. I get that double question mark is 46. And then I can use that to get that third one. Or I can use that theorem again. So angle 5 plus 75 is 134. I'll just use the 181. So measure of angle 5 plus 75 plus 46 is 134. I'll combine my like terms of 75 plus 46. The measure of angle 5 plus 121 is, and I don't know why I said 134, because that should be 180. The measure of the 3 angles in a triangle are 180. So then we'll do 180 minus 121, so that the measure of angle 5 is 59. Angle 4 is a vertical angle to 5, so that's also 59. And then I can find the measure of angle 3, because 61 plus 59 plus the measure of angle 3 is 180. So 61 plus 59 is 120. And then we'll subtract 120 from both sides. And angle 3 is 60 degrees. Right. So we're going to look at some things about congruent triangles and similar triangles. So let's look at congruent triangles first. So I have these ways to prove that triangles are congruent. So what that means is that a triangle is the same as another triangle. So if we know that all three sides are the same, then we have a congruent triangle. So like if we were given a picture and it told us that, hey, this side matched up with this side matched up with this side, and this side matched up with this side, that's telling me that all of those three sides are congruent. So that makes the triangle congruent. So that means all of the corresponding parts of the triangle would be congruent. If all the sides are matched up in congruence, then all the angles would match up in congruence as well. So we have something called side, angle, side. So that means two sides and the angle in between them are congruent. So it might tell us that those two sides are the same. It might tell us that these two sides are the same. And then it also might say that that angle that's between those two sides is the same. So side, angle, side. Or we could have angle, side, angle. So that means we could have two angles that are congruent. And then the side in between them is what's congruent. Angle, side, angle. Or we could have angle, angle, side. So angle, angle, side. Angle, angle, side. Or something called hypotenuse leg. So the hypotenuse is always across from the right angle. Always, always. Shorten that with hype. For hypotenuse. It does not matter that I just capitalized one and didn't capitalize the other. It would be the same. So the hypotenuse in any one of the legs, which is any of the other two sides of a right triangle, are congruent. So it could say that this side matches up with this side and that the hypotenuse is the same. All right. So let's look at some examples. Can we identify what kind we have? So I'm just going to list them up here. We have side, side, side. I know it's written small here, but side, angle, side, angle, side, angle, 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 side, and hypotenuse leg. So let's see if these have any of these congruent properties. So this first one, I see that there's two angles. And well, they are sharing this side. That side is the same. So I know that we have the side in between those two angles. So this would go with side, angle, side. All right, I know this side's the same as this one, and this one's the same as this one. And then this is the same line. So again, it's another side that's congruent. So this would be side, side, side. Oh my gosh, as I'm sitting here, I just realized I literally said angle, side, angle, and wrote side, angle, side. Oh my gosh. Angle, side, angle. Like I said that and wrote the wrong thing. Okay, this next one. We've got two angles and then a side that's not included. So that would be angle, angle, side. All right, when we see right angles involved, we should be thinking hypotenuse leg. So let's see. They do share the same hypotenuse, and one of the legs is congruent. So this does follow hypotenuse leg. All right, this fifth one, we've got two sides, but there's no way to know for sure if the third side is the same. So I can't do side, side, side. I know that these two angles are congruent because they're vertical angles, but we don't have a side, side angle. So I would say that we can't prove that it's congruent. So let's just say it's not congruent. All right, with number 6, these little triangles on these lines mean that these two lines are parallel. So we have a side, angle, the parallel. These are two parallel lines. We could count this line here as the transversal. This angle right here would correspond with this angle right here. So now we have an angle side angle situation here. All right, let's see, what do we have here? We have a side, an angle, and they share a side here. So that's a side angle side. This one, they share the third side. So this is a side, side, side. This has a right angle, so I want to think hypotenuse leg. So let's see, the hypotenuse, they do match up, and they do have another side length. So hypotenuse leg. Let's see, we've got an angle, we've got a side. And I have angles right here that are vertical, so those are congruent. So it looks like I have angle, angle, side. I've got an angle, and I know that they share a side. But there's nothing else that indicates anything else would be congruent. I don't have anything saying that there's parallel lines to prove that some angles are congruent. I don't have a right angle for hypotenuse leg. So I would say we don't know it's congruent. So we'll just say not congruent. And then this last one here. Again, this tells me that these are parallel lines, so we can probably use the idea that this is the transversal. So this angle here and this angle here are alternate interior, which are the same. So this is an angle side angle situation. Oh my gosh. Okay, it could be. I have side angle side. Because you could also say that this is a transversal here. So that this angle and this angle are congruent as well. So then we do have angle, side angle as well. So either one of those is fine. All right. So that means the triangles are congruent. So their corresponding parts are congruent. When we talk about similar triangles, they are not congruent. They are similar. So with these, the different corresponding parts are proportional, meaning there's some kind of scale factor. And the little letters, like the side angle, side angle type thing that we have for if these triangles are similar, we have angle, angle. We have side, 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 or side, angle, side for the similarity ones. So determine if these triangles are similar. So what we want to do is match up the corresponding pieces and see if the proportions are all the same. So how do we figure out what matches up since everything's not the same? This is what I do. There's 3 sides in a triangle. So there's a small side, and I'll even put this here. There's a small side, a medium side, and a large side. Okay, my handwriting is atrocious there. Try again. Small, medium, large. So if I look at this big triangle, I've got 4, 7, 8.06. And so it doesn't matter if I'm going from the big triangle to the small one, or if I'm going from the small to the big one. Because the big one's on the left, I'm going to use that as the top. So the smallest side is 4. The medium side is 7. And the large is 8.06. And so I'm going to make a proportion to that smaller triangle. So we have 2, 3.5, and 4.03. So the smallest is going to be 2. The medium is 3.5. And the large is 4.03. So what we're going to do is we're going to see, are these proportions all the same? So 4 over 2 reduces to 2. 7 divided by 3.5 is also 2. And 8.06 divided by 4.03 is also 2. So I can turn those question marks into check marks. They are all the same. So they are similar. So are they similar? Yes. If we're talking scale factor, we would have to know what direction we're going. Is this triangle the first one and we're going to the second one? Because then the scale factor will be based off of this ratio here. So because I'm going smaller, the scale factor is going to be 1/2. But if I was going from the small triangle to the big triangle, it's going to double. So it just depends on the direction. And this one, it didn't ask, so we didn't need to find that. All right, are these triangles similar? Find the lengths of the sides to prove your answer. So there is a triangular similarity theorem that says angle, angle. If 2 of the angles are the same, then the triangle's similar. So they both have a right angle, and then it tells me that these 2 angles are the same. So I do have angle, angle. And in a triangle, all the angles are going to add up to 180. So if these 2 are the same here, it's going to make this third one be the same. All right, so now we just need to set up the proportions. So I know the hypotenuse for both of these. So I'm going to use that proportion. So 30 is to 10. And then we can do each one individually. So I'll do y first. So y is going to match up with 8. So because I did the left triangle, then the right one, in the proportion I have to do the same thing. So I'm going to do y over 8. And then when I have 2 proportions set equal to each other like this, I can cross multiply. So 30 times 8 is 240. And that equals 10 times y, which is 10y. And then I'm going to divide both sides by 10. So y equals, and then 240 divided by 10 is 24. So y is 24 meters. I can use that same idea and say that 30 over 10, to use the same proportion, is 18 over x. So then cross multiply, we get 30x equals, and then 10 times 18 is 180. And then we'll divide both sides by 30. So that x is 6 meters. Right? So if we know they're similar, and we know the scale factor, so we're going from 3 to 10, so it's a factor of either 1/3 or 3, depending on the direction. We could have gone from that direction as well. So if I know that from 30 to 10 reduces to 3, that means this one times 3 would get over here. So 8 times 3 is 24. Well, look, we got 24. If we're going the smaller direction, then it's, instead of 3, it's 1/3. So we can divide by 3, and 18 divided by 3 is 6. All right, let's apply the idea of similar triangles to some situations. Okay, so I have a person who's 5 feet tall, and they are 50 feet away from the base of a tree. The tree casts a 50-foot shadow, and the person casts a 7-foot shadow. So what is the height of the tree? So what I see, without the drawings in there, is I see a big triangle. Tells me it's a right angle. And then I see a small triangle within. This would also be a right angle here. And then they share that angle right here. So that has to be the same. So I have angle, angle. So the triangles are similar. And so now I can just do the pieces. So if I separate it, you don't have to always separate it. With the big triangle, I know that this big length is 57. And I'm trying to find the height of the tree. And in the little triangle, I know that the 7 is for the shadow and the person is 5 feet tall. So I can set up a proportion. So I can say x is to 5 as 57 is to 7. And then I can cross multiply. So 7x equals, and then 57 times 5 is 285. And then I can divide both sides by 7 and get 40.714. And it keeps going, the decimal does. And it doesn't say what to round to, so let's just say 40.7 feet. Let's try another situation. So at a certain time of the day, a radio tower cast a shadow that's 180 feet long. At the same time, a 9-foot truck casts a shadow that's 15 feet long. What's the height of the tower? So very, very similar. I could separate it into 2 triangles, and I know that this bottom one is 180 feet, and I want to find this one. And then in the other triangle is 15 feet and 9 feet. So I can set up a proportion. X over 9 is 180 over 15. And then I can cross multiply. So 15x is, and then let's see, 9 times 180 is 1,620. And then I can divide both sides by 15 and get 108 feet. And so that's why I didn't go from a perspective of we know what the scale factor is, because sometimes it's not a nice number. It's not always going to be 5 times larger or 5 times smaller. So I set up the proportion and don't even worry about trying to figure out the scale factor unless it specifically asks. Because like in that last one, we got a weird decimal. So the scale factor was not something that was nice. So, yeah. All right. That is triangles. If you have any questions, let me know.